You've probably seen how you can type a sentence into an AI and get back this incredible piece of art, right? Or even a whole story. Well, now, that same magic is happening with motion. But, and this is a big but, there's a catch. What looks absolutely perfect on a screen can turn into a clumsy mess in the real world. So today, we're going to dig into some really cool new research that's trying to fix that very problem, closing that gap between our digital dreams and what's physically possible. All right, so first let's just talk about the dream scenario here. Because in the world of animation, virtual reality, AI has made some huge leaps. We're talking, of course, about text-to-motion technology. I mean, you can literally type in something like, a person kicks with their left leg, and boom, out pops this perfectly smooth, totally believable animation. This is what the experts call kinematic motion. All that really means is that it's purely visual. It only cares about where the joints are and how they're rotating. And yeah, it looks amazing. And think about it. The power here is just incredible. If you're an animator, a game developer, anyone working with virtual avatars, this is a game changer. I mean, complex movements that used to take hours of painstaking work, now they can be generated in seconds. It's just this massive creative unlock. But this perfect, clean digital world is about to have a very rude awakening. And that brings us right to the heart of the problem, what we're calling the robotic reality gap. It's that huge divide between what looks great in a simulation and what a real physical robot can actually pull off. So what happens when you try to bridge that gap? You take that beautiful fluid kicking motion we just saw, and you feed it directly to a real, state-of-the-art humanoid robot. I mean, it should just work, right? Yeah, not so much. And the reason why is actually pretty fascinating. That on-screen kinematic motion, it's basically a cartoon character. It can lean at impossible angles. It can jump without any consequence because it just completely ignores the laws of physics. A real robot, on the other hand, has to deal with stuff like gravity and friction and, that constant nagging need to stay balanced. And this image just says it all. What you're seeing in that bottom panel is a robot trying to pull off a move from a standard AI model. And what happens? It loses its balance, its feet slide right out from under it, and it collapses. That right there is the reality gap in action. The AI's perfect instructions were physically impossible. It was a set of commands that literally doomed the robot from the start. So if the AI doesn't get physics, the solution seems kind of obvious, right? We have to teach it. And that's exactly where this new research comes into play, with a really, really clever way to bridge that gap. The solution is a new framework called FISMO DPO. Yeah, I know, it's a bit of a mouthful, but the idea behind it is super elegant. Basically, it's a method you use after the initial training, and it's designed to give a standard motion AI a crash course in, you guessed it, real-world physics. And this is the key. Instead of just showing the AI what human motion looks like, this method forces the AI to learn what that motion actually feels like for a body that has to deal with gravity and staying upright. And how does it do that? By building a physics simulator right into the training process itself. Now, this isn't just some one-and-done lesson. Oh no, it's a continuous feedback loop that makes the AI smarter and smarter about the physical world over time. So let's break down exactly how that loop works. Okay, here's the play-by-play. Step 1, generate. For any given command, the AI comes up with a bunch of different motion options. Step 2, test. This is where a virtual physics coach steps in and tries to execute each one of those motions in a simulation. Step 3, rank. The coach scores all the attempts. The winners are the ones that are stable and actually follow the original command. The losers, well, they're the ones that fail. And finally, step 4, learn. The AI gets updated to prefer generating motions like the winners and to avoid motions like the losers. Simple as that. And this diagram from the paper really lays out that whole elegant loop. You can see the text prompt going in at the beginning, the AI generates a few options, then the physics controller, our virtual coach, tries them out. The results are then used to create these preference pairs. Basically, this one was good, that one was bad, which get fed right back into the AI to retrain it. It's a brilliant self-correcting system. So you might be wondering, how exactly does this coach decide what's a winner? Well, it's basically a two-part report card. First, there are the physics rewards. Did the robot stay balanced? Did its feet stay glued to the floor instead of sliding all over the place? But then, and this is crucial, there are the task rewards. After making all the tiny adjustments it needs to stay upright, Does the final motion still actually match what we asked it to do? This is so important because it makes sure the robot doesn't just, stand perfectly still to be safe. It has to actually perform the task. All right, so the big question, does all this intensive physics-based coaching actually work? Well, let's take a look at the results. And here we go. This is the same image we saw earlier, but now it tells the whole story. On the bottom, you have the original AI model, and it makes the robot completely wipe out. But on top, that's the same model after it's been retrained with this new method. And look, it performs the exact same dynamic motion, but this time flawlessly. The difference is, it's night and day. And the hard data tells the exact same story. You can see right here that the new method, FISMO DPO, gets a higher score for text accuracy. But what's really interesting is that jerk value. It's lower, dropping from about 47 down to 43.5. A lower jerk value means the final motion is way, way smoother. So it's not just more stable, it's actually a higher quality motion all around. Okay, but this might be the most impressive part of all. The model that they trained entirely in a simulation works on a real-world robot, the Unitree G1, right out of the box. No extra training needed. In this field, that's called zero-shot transfer, and it is pretty much the holy grail. It proves the AI didn't just learn a few tricks to pass the test in the simulation, it actually learned the fundamental principles of physics well enough to apply them to a real physical machine. So what does all this mean for the future of robotics? Where do we go from here? Well, this turns out to be a really significant step forward. Okay, let's just quickly recap the key takeaways here. For the longest time, this reality gap has been a huge roadblock, stopping us from taking those cool AI animations and making them work on real robots. This new method, FISMO DPO, bridges that gap by essentially letting the AI practice in a physics simulator where it can learn from its mistakes. And the results? We get robots that can pull off complex text-generated moves that are stable, accurate, and smooth. This is a really crucial step towards building those capable, general-purpose humanoid robots that, we've all been dreaming about. It really makes you think, doesn't it? We've just watched an AI learn an intuitive physical understanding of the world, pretty much the same way a toddler learns, by stumbling and falling over and over again. So if it's already starting to master the physics of balance and movement, what's the next human skill it's going to master?